Greetings and good day. My name is SANTHIRAGANESH RAVICHANDRAN and I'm here to present my UGP topic, which is 1 degree of freedom CFD analysis of bluff body encounter VIV. And now let's take a look. Here we can see the presentation layout where it is divided into 5 parts. Firstly, vortex-induced vibration occurs when a bluff body is exposed to a flow of fluid that produces vortex shedding at or near the structural frequency of the body. The problem statement of the study is the numerical analysis of 1 degree of freedom VIV is commonly done with static cylinders. The results obtained from such analysis are inaccurate. This is because there is no motion of the cylinder, as the motion is crucial to solving VIV related problems. To overcome this problem, a dynamic simulation should be implemented. The objectives of this research is firstly to develop the motion of a dynamic meshed cylinder in transverse direction. Secondly is to analyze the transverse vibration of a cylinder with different reduced speeds. The scopes of studies are as follows. Firstly is to do the literature review on existing 1 degree of freedom VIV analysis using CFD. Secondly is to design and develop the 2D CFD simulation for 1 degree of freedom VIV response in NC fluent with dynamic meshing. Next is to analyze the transverse vibration of the cylinder with different reduced speeds. And finally is to analyze the lift and drag forces and the frequency response of the cylinder with different reduced speeds. Here we can take a look at the VIV parameters. Lock-in occurs when the natural frequency of a body is in resonance with the vortex shedding frequency. Dynamic analysis of VIV is commonly done using CFD. This is because the dynamic meshing allows the movement of the cylinder when forces are exerted on the body. The results obtained from dynamic analysis is much more precise than static analysis. The model used in 2D VIV analysis is usually a simple rectangle domain with the cylinder inside the domain. The dimensions of the domain varies and it is with respect to the diameter of the cylinder. Almost all of the domains used in previous researches retain the similar shape but varies in size. For the 2D analysis of VIV, the meshing type is usually either quadrilateral or triangles or the combination of both. 2015 has used a structured quadrilateral mesh. For the methodology part of this study, firstly we can take a look at the flowchart implemented in this study. The computational domain generated for the study is in a rectangular shape. The cylinder study has a diameter of 0.1 meters. The upstream length of the domain is 6D, the downstream length of the domain is 15D, and the width length of the domain is 3D. For the simulation of the study, a structured quadrilateral mesh is utilized. Dynamic meshing is used to simulate the scenarios with boundary motion by using a user-defined function. The area around the cylinder is separated to become independent from the fluid domain to control the stability of the cylinder. This separated area is in the dynamic mesh zone while other areas are stationary. The dimensions of the separated area is 1.5D by 1.5D. Here we can take a look at the numerical settings used in ANSYS Fluent for this study. Before the simulations were done, the grid independence test was done. This is to determine whether the results of the simulation are independent from the quality of the mesh. So for the GIT, the mesh was tested with the Reynolds number of 10,000. The convergence is determined by checking the changes of mean drag coefficient and the RMS amplitude of lift coefficient for the sizes of mesh. The summary of the grid independence test is shown in this table. The highlighted mesh, which is mesh D, is used throughout the simulations. This is because that the values of drag coefficient and lift coefficient have very minor or no changes when the number of elements in the mesh exceeds 20,510 elements. To minimize computational effort, mesh D was chosen to run the simulations as efficiently as possible. The setup of the simulation can be validated by comparing to previous researches which are similar in nature to the study. In this case, the graph of non-dimensional amplitude AOD against the reduced speed can be used to compare the trend and the values obtained. The study by Tuan 2015 on the 1 degree of freedom VIV was used to compare and validate the study. Here in this plot, we can see that the orange marker is the values obtained in this study and the blue marker is the values obtained in the study by Tuan 2015. Thus, we can say that the setup is valid as the trend of the amplitude ratio values are quite similar. The differences in values are mainly because of the quality of the mesh and also the size of the domain used. And now for the results and discussion. Firstly, the system is simulated as a mass consisting of here we can see the properties of the cylinder and the iteration of reduced speed with respect to its Reynolds number. The range of Reynolds number used in this simulation is from 2000 to 14,000, and also the corresponding reduced speed is shown in this table. Time history response recorded for this study is for the drag coefficient, lift coefficient, and also the fast Fourier transform. Here we can see the drag coefficient against time and lift coefficient against time for the reduced speed of 5. Next, we can see the fast Fourier transform for reduced speed of 5. The next part of the results consists of the velocity and vorticity contours. Here we can see the velocity contour for reduced speed 5 in different times, where the cylinder is in the initial position and the topmost position and also the bottom position. And here we can see the vorticity contours of reduced speed 5 in different times, where the cylinder is in the initial position, the top position, and also the bottom position. The contours were captured to show the motion of the cylinder and also the vortex formation during the simulation run. Here you can see the animation of the simulation of reduced speed 5. From this animation we can see the movement of the cylinder. The numerical results which will be discussed is the amplitude ratio, the frequency ratio, and also the drag and lift coefficients. The variation of non-dimensional amplitude of vibration A over D as a function of reduced speed is presented with a fixed mass ratio of 2.4. The Reynolds number is increased proportionally with the reduced speed from 2000 to 14,000. The amplitude ratio from the study by Tuan 2015 and Pan et al. 2007 is also shown in the same plot with the same range of reduced speeds. The general observation that can be made from the plot is that the general trend of the amplitude ratio against the reduced speed of this study is similar to the trend shown in previous studies. The highest amplitude ratio obtained in this study is 0.53 at reduced speed of 5. From the SST K omega simulation by Tuan 2015, the maximum amplitude ratio recorded is 0.65, and the maximum amplitude recorded by Pan et al. Is 0.55, which also uses the SST K omega turbulence model. The observation made from the plots of amplitude ratio against the reduced speed from Tuan 2015 and Pan et al., where the highest amplitude ratio is recorded around the same region of reduced speed, which is around reduced speed of 5. There is a small drop in the values of amplitude ratio, where the reduced speed is more than 5, and in all of the results. Thus, it can be confirmed that lock-in occurs around the region of reduced speed of 5. This can be confirmed as the transfer vibration is at the highest when lock-in occurs. Next, here we can see the graph of a frequency ratio plotted as a function of reduced speed. From the range of reduced speed of 1 until reduced speed of 4, the frequency ratio is low, which is below 1. At reduced speed of 1, the frequency ratio is 0.31 and gradually increases with increasing reduced speed. Lock-in occurs when the shading frequency is equal to the natural frequency, or the frequency ratio equals to 1. At reduced speed of 5, the frequency ratio is 1.05. This shows that lock-in occurs around this region of reduced speed. Thus, it can be said that the frequency ratio is with agreement to the trend of the amplitude ratio. Furthermore, we can take a look at the force coefficients obtained from the study. Firstly, we can take a look at the drag coefficient obtained from the simulation results. From the plot of drag coefficient against the reduced velocity, we can see the trend of the drag coefficient against the reduced speed. It is clear that there are not much changes in the values of drag coefficient when the reduced speed increases. However, we can see that when the reduced speed is more than 4, the values of a drag coefficient increases and peaks out at reduced speed equals to 5. And when reduced speed is more than 5, we can see that the values of drag coefficient decreases. Finally, we can take a look at the values of lift coefficient obtained from this study. The plot of lift coefficient against reduced speed was done. Here we can see the trend of the lift coefficient against the reduced speed. The lift coefficient increases gradually from reduced speed equals to 1 and finally peaks out at reduced speed equals to 5, where the value is 0.62. When reduced speed is more than 5, we can see that the trend of the graph decreases with reduced speed. When the values of lift coefficient and drag coefficient are compared, we can see that the values of lift coefficient differs more than the drag coefficient. We can see that the minimum value of lift coefficient when reduced speed is equals to 1 is 0.31, whereas the maximum lift coefficient value is 0.62 in reduced speed equals to 5. Thus, we can say that the reduced speed has a larger impact in the force in the transverse direction. In a nutshell, we can say that the plot of lift coefficient against the reduced speed corresponds to the plot of amplitude ratio against the reduced speed. From the plot of amplitude ratio, we can see that the lock-in occurs at reduced speed equals to 5. In the plot of lift coefficient, the maximum value of our lift coefficient is at reduced speed equals to 5. The plots of drag coefficient and lift coefficient are in agreement with the plot of amplitude ratio against the reduced speed, as the transverse vibration is at the maximum when lock-in occurs. In conclusion, the overall simulations of the study show a reasonable agreement with previous researchers. The lock-in phenomenon, where the natural frequency and the vortex shading frequency is in resonance, occurred at reduced speed of 5. This can be confirmed by the analysis of the amplitude ratio, and the amplitude ratio peaked at reduced speed of 5. This translates to the plot of lift coefficient against the reduced speed, where the maximum lift coefficient value was at reduced speed of 5. Therefore, it can be concluded that the body experiences maximum transverse vibration when lock-in occurs during VIV phenomenon. Finally, here we can see the references that are used for this study. Thank you for listening to my UGP2 presentation.